In the last two videos, we've been busy building up two clock generators based on the 555 timer chip. These are what's actually going to run our Superscalar out-of-order processor as we start to design and build it in the future. Be sure to like and subscribe if you want to see how this project unfolds. So now we have two clock sources. We can single step the CPU through individual cycles with the button, and we can have it run on its own through this tunable clock. But to switch from one clock to the other, we had to pull out this wire and plug it into the other clock source. What we really want is a switch or a bunch of buttons that we can use to switch from one clock source to the other. A single clock wire will then carry the selector clock to the CPU. Let's take another look at that 555 timer. There is this set reset latch in there that is hooked up to the comparators. When the lower comparator triggers the set input on the latch, the output goes to high and stays there. And when the upper comparator triggers the reset input, the output goes low. Now instead of those comparators, we could hook up two buttons to that SR latch, which would allow us to push one button to switch it over to 0, and the other button to switch it over to 1. As it turns out, we can build an SR latch pretty easily ourselves from just two NAND or NOR gates. All we have to do is take two such gates and wire each output up to an input on the other gate. The remaining two inputs become the set and reset lines of the latch, active low for the NAND case and active high for the NOR case. Setting this up in this way creates a positive feedback loop, which causes the outputs to stay at whatever level they are when the reset and set lines are inactive. If we trigger the set input, the upper output goes high and the other low. And if we trigger the reset input, the upper output goes low and the other high. Triggering both inputs at the same time is unstable and can produce a random result, or even worse, cause the SR latch to oscillate. We'll use two more buttons as the input to our SR latch. I'll be using NAND gates, which have active low inputs. So we'll want to make those buttons active low as well by connecting them up to ground and adding a pull-up resistor to VDD. Now, for the NAND gates, we'll be using our first of many logic chips in this build. The 74HC00 chip contains 4 NAND gates with 2 inputs each. Let's place this right next to the buttons and wire up pin 14 to VDD and pin 7 to ground. For our SR latch, we'll use 2 of the gates and connect each output to one of the inputs on the other. So let's connect the first gate's output on pin 11 to one of the inputs of the second gate on pin 9, and the second gate's output on pin 8 to an input of the first gate on pin 12. That leaves pin 10 and pin 13 as our set and reset inputs. So let's connect these to the buttons. And we'll also want some LEDs right above the buttons to show which mode is currently selected. Conveniently, there's a 1-row gap between the button terminals that can neatly hold the LEDs. Now, pushing a button will cause that input of the SR latch to go low, and correspondingly the output of that gate to go high. So we want active high LEDs, which we get if we hook the anodes, that's the longer terminal, up to the chip through a resistor, and the cathodes directly to ground. That should be all that's needed. Let's hook up power and see if this works. So it starts up in some random state, and we can see one of the LEDs is lit up. If I push the buttons, the corresponding LED will go on and stay on until I push the other button. Awesome, this is working. It's important to note that we don't care about the buttons bouncing in this case, because as soon as the button makes contact, the output will switch to that state and stay there. And any additional button presses or bounces don't have any real effect. It's already in that state and it will stay there. Let me quickly clean this up a bit so we don't have these cables all over the place. Alright, so now we have a bunch of radio buttons to switch between two modes, and the SR latch gives us two convenient outputs to work with. Now let's use those outputs to select one of the clock signals as the CPU's clock. What we want is a basic clock multiplexer that picks one of the incoming signals and feeds that through to its output. Now there's a whole bunch of ways we can build multiplexers. For example, using dedicated MUX chips, or tri-step buffers, or plain old logic gates. Now, from our clock selector, we're getting an output signal for each clock source. The output is high if that clock should be selected, and low otherwise. That kind of signaling is also called a one-hot encoding, because there's a 1 indicating which mode is active, and there's only ever a single 1 in the output, all the others are 0. Since we've already used a bunch of NAND gates to build the clock selector, let's see if we can't also build the clock multiplexer out of NAND gates. So here's what we're working with. We have 4 inputs, 2 are the clocks we are supposed to pick between, and 2 are the signals coming from the clock selector. Now, since the selector outputs a 1 for the clock that should be selected and a 0 otherwise, we can AND each clock signal together with its select line. That will cause the selected signal to show up at the output of its AND gate, because the select input is high, and all other AND gates to produce a 0, because their select inputs are low. This basically masks all clocks to 0, except for the one we have selected. And since all except for the selected clock are 0, we can use an OR gate to combine the outputs of all AND gates into a single clock output. Now, whichever clock input is selected will make it through its AND gate and then pass through the OR gate to the output. This AND/OR structure is a very common way to build multiplexers if you have such a one-hot encoded select signal. We're only using 2 inputs here, but this works for any number of inputs you could want. An AND gate between each input and its selector, and a tree of OR gates that reduce that down to 1 output. Now, these are AND and OR gates, which isn't too bad because there are dedicated logic chips of the 74HC series which contain AND and OR gates. But we can play a few logic tricks to make plain old NAND gates do the same job for us. A NAND gate is just an AND gate with the output inverted. So if we want to replace those AND gates in our multiplexer with NAND gates, their outputs get inverted, which is indicated by that little bubble here. Now we'll have to make sure that we pick an OR gate that first inverts the inputs back, again indicated by those bubbles, before it does its OR operation. So all we did was add a bubble at the output of the AND gate to make it a NAND, and a bubble to the OR input to flip the signal back right side up again. Now for that OR gate, let's quickly pull up De Morgan's laws. An AND gate with its inputs flipped is a NOR gate, but also an OR gate with its inputs flipped is a NAND gate. So that OR gate we had with its inputs flipped was actually a NAND gate in disguise all along. And there you go, we can build our AND/OR gate with just plain old NAND gates. Now we need 3 additional NAND gates for this, and the 74HC00 chip we already have on the board only has 2 left. So let's add another one just for this multiplexer to keep things neat. Also, let's hook up power and ground right away. First, let me connect the 2 clock sources to one set of the inputs on the first 2 NAND gates. And then connect the corresponding selector outputs to the other set of inputs on those gates. That takes care of the NAND gates at the input. Now their outputs need to feed into the third NAND gate, which will produce the final value. And that should be all that's needed. Let's hook up one of the LEDs to the output of our clock multiplexer, and thus get rid of the other one, which is no longer needed now. Also, let's connect the clock for our counter circuit at the bottom here to this new clock output. Let me power this back up and see if it works. So again, this starts up in a random selector state, but if we push the left button, we can choose the single stepping clock. That allows us to produce single clock pulses at the push of a button. And if we push the right button, we can choose the free running clock, which we can have go faster or slower by tuning this resistor here. Now that we've seen that this works, let me clean up these cables a bit so the breadboard stays nice and neat. That's awesome. With this, we have a single proper clock line for our CPU. And we can select whether we want to step it through individual clock cycles manually, or have it run at a tunable speed just by pushing these buttons here. In the next video, I'd like to look at how we can generate a reset signal for our CPU, which is fairly closely related to all this clock business we've been looking at so far. Also, it would be great if we could get the clock generator to power up in the single stepping mode, so the CPU doesn't just run away as soon as it's powered up. Thanks a lot for watching, like and subscribe if you'd like to see more of this, and see you next time.